Okay, so this means that we can do nonlinear Lyapunov analysis. Right, so let's say I have a polynomial dynamical system, right? If I'm willing to write V as some polynomial, let me write it like this, where M is my combination of monomials. Okay, so if I write a grab bag polynomial Lyapunov function, and I want to search for the Lyapunov function by searching over the coefficients of the Lyapunov function, then I'm going to be able to write down an optimization problem which says, find me some parameters alpha such that V is greater than 0 and V dot, which remember is partial V, partial X, which will be polynomial. The derivatives of the polynomial are still polynomial, times P of X is less than or equal to 0. Yeah? So I don't have to be mysterious or magical about it. I can just say, all right, solver, find me a Lyapunov function that matches all these conditions. And I'll put the caveats on it in a second here. And basically, if there's one that exists, the solver will tell me it exists. Or it'll give me the Lyapunov function. If it doesn't exist, it'll say it doesn't exist. Or it could potentially say numerical errors. Or it could say, blah. If you ask for too big of a system, right? If I try to do this just brute force on Atlas, for instance, it'll go off and try to allocate all the memory on your machine and your neighbor's machine, and then just never respond. That's the other failure mode. But for pretty decent sized problems, it'll tell me my Lyapunov function. Yes? That's pretty cool. Now this was for global analysis, so we have to do more if we want to do local analysis. But does that make sense? Yes?
So does this only work if P of X only has one root?
Nope.
Oh. So.
Nope, you can have, you could have, so you guys start getting into the subtlety of whether this is strictly negative definite or not. So if I have, so let's say something that has two fixed points, that would be the roots of P are the fixed points, right? Then of course I'm not going to be able to prove global stability of this, but I could still prove something that says with Lassalle's argument, right, that the sum of the invariant set which contains both of those fixed points is stable, right? If you ask for something to be strictly positive or strictly negative definite, then you'll fail on that, unless you can do things like tell it to ignore a point. And there's all kinds of variations of this. So the short answer is that's not a problem.
How general is it that all systems will be polynomial? Good.
I'm going to address that in the last few minutes. Yeah? Not all systems are polynomial. You can Taylor approximate any system. And in fact, that's only partially a cheeky answer. We actually do that a lot, right? So it's if it's smooth, if the nonlinear dynamics are smooth, non-polynomial, you could Taylor approximate it and do fairly well. And you could even put bounds on your errors of your Taylor approximation if you want. But I'll convince you by the end that actually robots are polynomial. Okay? So, or I hope to convince you. Okay, so this is for global stability analysis. The other big thing we did was region of attraction analysis with the Lyapunov functions, right? So how do I do region of attraction analysis with this kind of a tool, right? This is a challenge for you, right? So I'm telling you that for our current purposes, there is an oracle that you can ask. You can take your polynomial to this oracle and say, oracle, is this polynomial positive, greater than or equal to 0 for all x? Right? And he or she will say yes or no. That's our abstraction for now. Okay? You can take the polynomial there, you'll get a yes or no answer. But now I want something that, if I want to prove that something's stable over, if I know it's not stable globally, right? I know the answer is going to be no if I just say, can you find me a lyapunov function for the entire state space? The oracle will say no, right? So what if I say, okay, what about for this part of state space? Can I find a lyapunov function for this part of state space? How do you rephrase your question to the oracle so that their question answering system will give you what you want? Yes?
Can you multiply your polynomial by a column that put it at 0 like in one slot?
You're almost right on. So what Audrey said is that basically if I have a polynomial and I know that it's, let's say, negative someplace, maybe if I just multiply that by 0 everywhere in the place that I don't care about, then my oracle will say yes. Okay, but the problem is multiplying by 0 and then non-zero somewhere, that's not something I can represent with polynomials. So the idea is very good, but so in order to ask the oracle, to be a valid question for the oracle, you have to ask it in terms of polynomials. Right? So how can I take my original question and sort of zero out the things I don't care about, but with a smooth function? Right? Do people get his idea? Was just zero out the things I don't care about, right? It's basically exactly that, but I'm just going to try to. I'm going to ask the oracle, find me a smooth function, right? I'm going to, give me a function which I can make positive. I'm going to give you some extra free variables that will make something positive where I don't care, but won't change my answer in the part I do care about. That's the idea, and it's a Lagrange multiplier kind of idea. So how do I do regional analysis? It's via, so different people call them different. I think it's most simple to call them Lagrange multipliers. It's also known as the S procedure. It's also known as positive Stellensatz. This is from the algebraic geometry view of the world. That's the problem with when you find these deep, beautiful connections between different fields, you get weird names for things, I guess. Positive, I think I wrote that right. I told Anya and Michael that this is my biggest test for the lecture was if I could write that correctly. All right, so the idea is if I want to ask, is P of x greater than or equal to 0 for all x where let's say g of x, some other polynomial, is less than or equal to 0. Right, if I can define my region with another polynomial, then it's enough to ask, is for all x, is P of x plus lambda x g of x greater than 0 for some polynomial Lagrange multipliers. I'll show you a specific example of this. I'm going to make up some new polynomial lambda of x. Okay, and the idea, this thing is only ever positive. The thing I want you to understand is that when g of x is less than 0, then that means proving this is positive only got harder, right? Right? When g of x less than 0, it's only harder to prove. So it's a sufficient condition again. And then when g of x is greater than 0, then I can make it arbitrarily, even if p of x was negative, I can come back and add sufficient positivity to make this whole thing be positive. So it's almost exactly what Audrey said, where I'm going to just add in something else in the parts I don't care about to make the oracle say yes or no the right way. Yes?
These things are not handled non-polynomial constraints. Like, why not just specify your lambda as your g of x as a constraint as opposed to
Well, I thought I understood your question, but the second part threw me. So you're saying, so it is the case that we're magically relying on polynomials here.
Right, but you want to search over space where these polynomials are less than 0.
Yes.
Why not just specify that as a constraint and let the optimization deal with it, as opposed to specify it as a multiplier?
Okay, really good question. I think I understand. So, so this is not a constraint on the decision. X is not a decision variable. No. This is a subtle answer, I think, and I want to make sure we get it right. There's in the sums of squares problems. I'm going to flip back to the previous page here. Okay, there's two sets of variables flying around here. There's my decision variables, and I can put constraints on my decision variables. And then there's these indeterminates, okay, which are something that these things have to be hold for all possible x. So I can't. So that's a separate thing. So I could put linear constraints on alpha, absolutely. But the only question I've learned how to ask so far is how do I ask for something for all x, for the indeterminates. That's what my oracle's capable of, which is a little screwy, but that's what we got. That's what we can map to the semi-definite programs. And it's with tricks like this that we can accomplish what you're hoping for. Okay, so let's do, does that make sense to people? Yeah? All right, let's. I mean, I think this is something that you kind of have to chew on, but it sort of makes sense that I'm going to draw a picture of it in a second. All right, so let's put it to work. So let's say I have x dot equals negative x plus x cubed. It really is my favorite example. This one here, right? It's so clear. Okay. Right, so I want to, remember we said last time that I was able to prove stability with x squared, and it turned out that v dot, it gave me exactly the region of attraction I wanted. Let's ask sums of squares to do that for us, okay? So I'm gonna formulate this for you. I'm balancing how much time I have left here. So here's how to make it a little bit concrete. I want to find, I know what v dot is. It was 2x squared plus 2x to the fourth, right? Minus 2x squared plus 2x to the fourth, yeah? I'm going to make a new polynomial, which is going to be my Lagrange multiplier. Call it C0 plus C1x, C2x squared. Now, it stinks, but to write it in the algorithm, I have to pick the degree of this, and this one I can't tell you there's a good answer for necessarily. There's some heuristics, but you just have to guess how much you need in the what degree you need here. If you fail, you can increase it, but you have to guess that one. Okay, and I'm going to ask that, I'm going to say find the coefficients C subject to this thing being negative semi-definite in the region I care about, which is equivalent to saying the part I care about is when v is less than 1, right? The true ROA I know happens to be whenever v is less than or equal to 1. So I'm going to say, can I prove that by finding some Lagrange multipliers which demonstrate that this thing is actually strictly less than or equal to 0 in that region. Okay. Okay, so let me step you through this a little bit here. So I'm going to say there's some symbolic variable, x, some variable that I want to be my indeterminate. Okay, I construct my program, I say that x is an indeterminate. That's something that, whatever I prove, I want to prove for all x. I define the dynamics in terms of that, and I define my Lyapunov candidate here in terms of that. Okay, and then I'm going to add in, I'm going to say I've got some decision variables here. They're free variables, c. I'm going to make my lambda, which is exactly what I wrote here. It's just c times some monomial vector x. Okay, and you're going to have this code, so okay, but I'm going to add this constraint. Oh, I forgot to write here that I also have to say that lambda x greater than or equal to 0. Okay, so lambda has to be positive, and then my v dot plus lambda 1 minus v, it's got to be positive. Now, because there's this gap between negativity and strictly negative definite and negative definite, and positive negative semi-definite, I'm going to add in a little. I'm going to ask it to be not just negative, but I'm going to ask it to be smaller than some slack pair. I'm just going to add this in for numerics to have an objective, to say, actually try to be really as negative as possible. And then I say minimize, make that as small as possible, and display the results. And I'm going to plot a couple things for you when it runs. Okay, so here's my x cubed. This is v dot. You already know that it's negative only up between -1 and 1. It couldn't be more, right? How do I prove that? I find a Lagrange multiplier, this lambda, which is some positive function, which when I add it together, now this is v dot plus lambda 1 minus v. When I add it in together with this, it makes a function which is in fact negative everywhere. Okay. Now I'm gonna let you chew on that by putting it in the notes and everything. But this is, it turns something that is not negative everywhere. It goes off here, and it adds in something that kills these terms, so that I can use my oracle to prove stability. Okay. Hope that makes sense. There's tons of examples we could do from here. One of my favorite ones here is the van der Pol oscillator. Okay, so it turns out that you can even search for v. So in that case, in the region of attraction case, I just tried to search for the Lagrange multipliers, but you can search for the coefficients of the Lyapunov function and the Lagrange multipliers at the same time. Okay, and we've packaged it all up for you. There's going to be problems that are going to force you to think about it, but we've also made it very easy in Drake to do it. There's just a method you just call, give me the region of attraction, and it'll do everything for you and spit out the region of attraction. And for pretty complicated systems, and does some things to make the numerics right. Okay, so the van der Pol oscillator is this cool system. This is actually the time-reversed van der Pol oscillator. The oscillator, by default, will just it happens to be a well-studied system that has this stable periodic behavior in the phase. This is Q and Q dot, okay? All that matters for the purposes of this is that it happens to be a system that's polynomial, which is good, that has a known region of attraction. If I time reverse it, then this region here from numerical simulation, I know is the true region of attraction to the fixed point. I run my region of attraction sums of squares algorithm, and what I get is something that whenever I get an answer, it's guaranteed to be sufficient, but it's not guaranteed to be tight. It's always, every decision is made to be conservative, so that if you get an answer, you can trust it, but you may not get the biggest answer. So what you get is an inner approximation here. This is now, it searched for a fourth order Lyapunov function, polynomial Lyapunov function, which is an inner approximation, but as big as possible inner approximation that proves stability to that point. And this is what you get. This is the true region of attraction. This is the estimated region of attraction. Okay? Extremely, extremely cool. Okay, yes?
Frequency expand the slack. What is the slack in the previous code again?
So instead of asking for v dot to be just less than or equal to 0, I said I'd like v dot to be as negative as possible. The way I did that is I said v dot plus some slack variable times x squared is less than 0, and make that slack variable as negative as, or as positive as possible.
So we just randomly choose that function like to make it a little bit.
Yeah, x squared is just some function that, because I know it's got to be 0 at the origin, and then try to find something that pushes it down. Just to put a weight on it to give it an objective. Okay. So we're going to see this again in a couple different times throughout the course. There's lots of things to say about this. There's lots of different formulations. Some of them are beautiful and simple. Let me just say that rigid body dynamics are in fact polynomial, and I'll convince you of that next time. Okay. And the other thing I want you to understand is that the case that we talked about before, if I have a nonlinear system, and I were to do, for instance, LQR to stabilize the system in some region. You've done this on your problem set. Wasn't it annoying in the Acrobat to have to pick the region when you turn on your LQR controller? That's annoying, right? You don't have to do that anymore. You can call region of attraction. It'll tell you a region where it's guaranteed if I were to turn on the LQR controller now, it'll work. And you can use that as your detector to flip it in, okay? So there's lots of different ways you can put these together and make it work. And we'll have more examples and more complicated situations later. Also, I should say, Ani and Michael, your TAs, are two of the very best people in the world to be asked. If you have any questions about this, they're the experts. So you should absolutely ask them and use that resource if you're interested in this kind of stuff. See you next time.